Hello, I'm Bill Mills with Lenaro. We're going to talk about Devicetree from 4 different perspectives today with 4 different speakers. So first off, Andre Kolodny is going to talk about system Devicetree in context. Why is it important? Why do we need it? Then Stefano Stabilini is going to talk about what is system Devicetree, what's current and future activities. Kumar Gala is going to talk about Zephyr and RTOS and Devicetree usage in those. And then finally, I'm going to talk about standard Devicetree in standardized Linux boot. So what is Devicetree? Devicetree is a pure data structure that describes the SoC and the board hardware. It's been used in the Linux kernel for a long time. It started on the PowerPC, but ARM's been using it since 2011. It's supported by a lot of different architectures, and there's a lot of different software projects that have picked it up and are using it and still in use today. So what is system Devicetree? System Devicetree is a newer concept that takes Devicetree and extends its perspective so it can describe bigger parts of the system, describe the point of view from multiple independent CPUs, independent OS components, so that you can really get the whole system perspective. One valid question to ask is, why use Devicetree today? Many people know that ARM servers are using ACPI. So if ACPI meets your needs, by all means use it. But we believe that there's a number of use cases around embedded systems where ACPI is not necessarily a good fit, and Devicetree can fill that need. Devicetree is more flexible and nimble, which is both a blessing and a curse, as we can talk about later. But so there's still a role for Devicetree to play. Even if you envision ACPI being used, we believe that there's a role for system Devicetree regardless. And then there's a number of standardizing activities around Devicetree. ARM SystemReady standards has a flavor called IR, IoT Ready, that's Devicetree based. In the embedded base boot requirements effort has been underway for a couple of years now and are standardizing this.
It is a small turtlebot robot running ROS2, and it shows a quite complicated example of the mixed critical safety system. So turtlebot has a LiDAR ultrasonic sensor for the environment sensing. It has some control algorithm running which produces an output to the actuators and the wireless connection to the road. So here you can see a dashboard. And on the dashboard, you can see that we have deployed 4 operating systems. So you have 2 instances of the real-time operating system. Then behind that, you have behind this screen, you have another instance, and then you have a Linux running, which serves as a gateway to the outside world. Plus, underneath of all these guest operating systems, a real-time hypervisor running. Next slide shows a detailed architecture diagram. System contains of ARM SoC with 4 cores. You can think of Raspberry Pi 4 or similar board with various peripherals. You see UART, GPIOs, USB where LiDAR sensor and motor control board are connected, SD card, Wi-Fi, and you see that the guest operating systems, they are mapped to cores not equally. So 2 OSs run on 1 core, then 1 OS running on the 2 cores, and another 1 OS runs on the separate core. So different peripherals are exposed to the cores via hypervisor, and besides that, you also have a way of communication between guest operating systems where virtual network interfaces need to be created. And this actually produces big challenges to describe and to configure such a system. So system configuration is spread via different instances. It's a hypervisor, a real-time operating system, Linux. So you need to configure CPU, amount of RAM, network, peripherals, configuration formats on each operating systems are not compatible. You have, for instance, proprietary Devicetree for the hypervisor, VxWorks Devicetree on the RTOSes, and it's a coincidence that this real-time operating system has Devicetree. So other operating systems does not even have Devicetree, and values are hard-coded. So on the Linux, you have a standard Linux Devicetree, and it causes like difficulties to check the whole system for consistency, to modify the configuration if modifications are needed. You need to define values in different places. And I have given an example of SMP system, but you have also AMP systems where, for instance, you have R5 and you need to configure such a system. So as you can see, it's quite difficult and error-prone. And next speakers will explain how Linaro wants to address this challenge.
Hi, I'm Stefano Stabellini, and I'm the virtualization tech lead at Xilinx. System Devicetree addresses these points by expanding on the Devicetree specification that's used to describe hardware for one operating system. System Devicetree describes a whole SoC for multiple operating systems. So it can describe an SoC with 2 or more CPU clusters. For instance, a Cortex-A cluster where a RTOS like Linux runs, and a Cortex-R cluster where an RTOS is running. It does so by introducing CPU cluster nodes, and you can see an example on the top right side of the slide. System Devicetree can also describe differences in address mapping for these CPU clusters, and you can see how it is done with the address map property again on the slide. Different in address mapping can be such as a device is visible only from one cluster and not the other, or a device is visible at different addresses as the different clusters. The other major area where System Devicetree help is the whole AMP configuration of the system. Software, what is running where, which execution level. It does so by introducing the concept of execution domains. And you can see an execution domain on the bottom right side of the slide. An execution domain is a collection of hardware resources necessary to run a software component, such as an operating system. So it includes the CPUs where the software is running on and the execution level. It includes memory areas that are needed by the domain, and as well as a list of devices that are uniquely accessible by that domain. In this example, the CAN bus controller. Finally, another important piece of the System Devicetree world is Lopper. Lopper is a Python tool that takes a System Devicetree as input and generate multiple traditional Devicetree as output, one for each execution domain. So the System Devicetree is input, and you get as output a traditional Devicetree that you can give to Linux unmodified, and then Linux can boot, or Zephyr, or Zen, or any other OSs. I'm gonna spend a few words on a newer development on that's remote proc supporting System Devicetree. Remote proc is a communication and lifecycle management protocol. So Linux typically uses remote proc to boot up and communicate with a remote coprocessor like a Cortex-M or an R5. You can see the traditional way of describing a remote proc connection here on this slide, and it's not very intuitive. It's very informative, but it's not for humans really easy to understand. As opposed to the System Devicetree description that you can see here, thanks to the system-level view with multiple execution domain, one domain with Linux on the Cortex-A's, another domain with Zephyr on the Cortex-R's, it becomes much more natural and intuitive to describe remote proc. In this example, in fact, it only takes Resources uniquely assigned describes to the access list, like the API mailbox to the Cortex-A domain. And some resources that are shared, and then you can see the resource group on the top right side of the slide, including 4 memory regions and the TCM, that's a little special SRAM region. The resource group is shared between the A53 domain and the R5 domain. That's all it takes, plus a couple of flags, to specify a remote proc connection at the system device tree level, sharing of resources and uniquely assigned resources. Then Lopper can take these as input and generate the traditional remote proc device tree as output, as understood by Linux and other OSs. I uploaded a full system device tree example online. You can check out full description of assigning board plus multiple domains. And in the next 6 to 12 months, what we're looking at is introducing bus firewall support in system device tree. Bus firewalls are these little components that can block the DMA transaction on an SOC level, and therefore they can be used to protect domains from other domains. We're also looking at hypervisor bindings. Since the very beginning, domains were meant to be not just AMP domains, but also hypervisor virtual machines, especially static hypervisors. And finally, YAML. We want to be able to describe execution domains in a simpler way, more intuitive, using YAML, still correspondent to the device tree description you have seen on these slides.
Hello there, I'm Kumar Gal. I'm the technical lead for the Monaro IoT and Embedded group. I was going to talk a little bit about some of the work we've done over the last few years around use of device tree on RTOSs and specifically Zephyr. So in the MCU space and RTOS space, we have some of the same type of issues and problems that you would see in a general purpose processor or general purpose OS, even in the microcontroller space. So wanting to have the ability to describe systems in a vendor neutral way, having something that conveys hardware configuration to different software environments, so between an RTOS and maybe middleware, and then having very similar type of hardware systems of asymmetric. So we have, MCUs that have multiple cores of different types, of having things like trusted execution environments, and even having, as it's been mentioned earlier, heterogeneous systems where we have, MCUs embedded in larger SOCs and so forth. So device tree is a very natural concept to utilize in this environment. What's distinct or unique to the environment is the footprint concern. And so the classical kind of use of using device tree at runtime, having a blob, having code to parse that blob, doesn't really fit the MCU use case because of footprint concerns. To give a quick example, the BBC microbit has 256K of flash, 64K of memory. And you can kind of see the numbers here where that you end up using a lot of your resource just for device tree if you're using the classical sort of model. So instead, what we looked at was to use device tree as a common representation and then do code generation out of that. So to talk a little bit about the code generation we've done in Zephyr over the years, it's definitely improved and changed since we introduced it back in 2017. We've always kind of tried to support multiple portability with the code set and generation tooling. So we utilized Python as the base of that tooling. And we've tried to keep what is the set of scripts and tools that we've written here not be Zephyr specific so that we could pull them out in the future. And that's something we're looking at doing. And I'll talk about it in a second. So the tooling is kind of broken into 3 pieces. What we have first is a pure DTS parser that kind of just gives a Python view of a DTS file. Then we have a script that takes that sort of data representation and gives sort of a more device model view, so understands things like registers and interrupts and clocks, and so it gives you a bit more structure to that data. And then finally, we have the script that sort of takes that view and actually generates out a set of defines that can be used. And here's just a very simple example where we have a UART node, a register address and size for that node, and then kind of an example of the macros language that we kind of have that we can use to extract that data from the set of defines. And so we have a way of referencing the node. So in this example, we're using the node label UART 0, and then we're asking for the reg adder. And there's a much more rich set of macros and so forth that I've got some pointers to here. And so this just gives a quick graphical view of sort of how the tooling works and so forth. So we have sort of our source files for the DTS. We have a set of bindings that are today Zephyr specific that we intend to work towards trying to unify with some of the work that's going in the Linux bindings. Those kind of are input to the tools to understand the structure of everything, kind of the set of scripts that I mentioned, and then out from those scripts, we get a set of defines. And then there's these macros that you can sort of work with those defines to give an interface, and there are pointers here that you can look in more detail. So what are we up to next? So we're kind of moving from being able to describe sort of traditional MCUs of a single core MCU that's standalone and one software environment to kind of wanting to take advantage of the system device tree work that's been talked about and extending that into the MCU space and looking around trusted firmware and the trusted execution environment is kind of one of the first use cases we're thinking about looking at with system device tree. In addition to that, kind of as Stefano mentioned, that there's the work going on around the bindings for system device tree. And so we want to kind of make sure that the MCU use cases and the way MCU hardware is managed in that binding definition and working with a group there. We're also looking to work with the Lopper tool, which is what is the sort of tool today around system device tree, and how we can glue some of the work we've done today, pull some of that out of Zephyr, and have a bit more common base to build these tools around and work for going forward. And then finally, kind of towards that trusted firmware of really showing an example of how this would work for a real system.
All right, so let's talk about device tree and standardizing Linux and other OS boot. So we talked about EBBR and SystemReady IR in the introduction, but this is really an effort to standardize the boot flow for higher level operating systems, provide a clean delineation between the firmware and the OS layer, whether it be the OS kernel or a hypervisor. The embedded systems today, still the boot flow is very mixed, very messed up, very inconsistent, I should say, and it varies quite a bit, despite the previous efforts to standardize this. And at the same time, we're getting new requirements. So we want to standardize the methodology for doing secure boot, make it distro compatible. And when we do that, the DTB data the signature of that needs to be verified by somebody in the boot flow. Likewise, if you're doing measured boot, the DTB data needs to be measured into a PCR. So one of the aspects of the DTB boot flow, one of the debatable aspects is who owns the DTB? Should it be the firmware or should it be the OS? There are pluses and minuses to both models. The OS is sort of the current model, but the firmware kind of makes more sense. So what we're trying to do is do a hybrid model where the firmware always provides a DTB, and as time goes by, we will get better at making that work out of the box more often. But at the same time, the OS has the capability, when it knows the hardware and thinks it knows better, can override that DTB, and all the hooks to make that work properly are in the architecture. So the current activity is basically three things. So Varesh Kumar is working in the upstream kernel to allow to do the work in the make file and other things so that we can have overlay source files in the upstream kernel. Up to this point, there's really been no upstream place for overlay source files. Now, these overlays are still applied by the bootloader. Applying those at kernel runtime is still something for later. The second thing we're doing, Heinrich Schuchart has done great work in defining a API, a UEFI-based API that can reside in the firmware that the OS boot managers can call when they do want to override the DTB, and then the firmware can then fix up MAC addresses, serial numbers, and things like that. Thirdly, we're working on a proof of concept so that it's QEMU based, but we're doing it in a way that can be hopefully replicated on real hardware that really shows the DTB coming from the firmware in a real system with grub in the path, having the DTB independently updatable, and prove that all that works. So what we're trying to do in the next 6 to 12 months is we want to finish that work with the grub being able to do firmware fix up. We want to start doing DTB ABI stability, where we test the very latest kernel against DTBs from 1 or 2 years ago. And so we start detecting immediately when changes are made to the upstream kernel that will break DTB ABI compatibility. We'll start small and build on that. There's been effort. There was a previous effort to try to get everybody to put all the Devicetree source in one place. That's kind of been rejected by the community, at least for now. And so what we want to do is provide tooling to the project maintainers so that they can detect when their project is out of sync with other projects that they may consider more upstream. So this is an honor system. It's a tool that the project maintainers can use to help them know. And then finally, we're working on defining the DTB file and memory format enhancements. There's been a lot of enhancements suggested over the years. Not all of them will be make it in, but we really are hoping to have a plan of record for the next format. All right, so I hope that you agree that there's a lot of stuff, exciting stuff going on with Devicetree, both innovation and standardization. We're not taking any questions in this session, but there is a bird of feather session immediately following this. And so we look forward to taking your questions during that bird of a feather. We'd all like to thank you for your attention today.